Okay, so we've just heard a lot about lift station assessments. We're going to shift gears a little bit now and talk about the force main side of our lift station and force main segment. Our next presenter is Kathy Morley, a senior project manager for RJN Group. Kathy, it's all yours.
Thank you, Zach. So this is a case study for a force main in Hanover Park. It's interesting because this force main was only installed in 1999, so at this point, 18 years old. It's 16 inches in diameter and it's almost 17,000 feet long, so 3.5 miles. So a significant force main, and it's through residential areas, forest preserve, landfill, river, and even underneath a lake wetland area. There are some major variations in elevation. The reason that we're talking about this, as you can see here, we have this really long force main that starts residential, but then once it gets into the forest preserve, and we've taken off the aerial just for clarity, but you can imagine that this, once we leave the residential area, this is really pretty difficult to get through. And they had a force main break here in August 2013. It was an emergency repair. It was right adjacent to the DuPage River. As you can see, it was some 100 feet away. It was on a Friday afternoon, which in itself was a nightmare to get a pipe. And so they did replace 120 feet of bare pipe of ductile iron. It had no coating, no nothing on it. So the village's major concerns was, well, why did this happen? At the time, this pipe was only 14 years old. Are there other parts of this very long force main that are also vulnerable? And what the heck would the cost be to correct this, or to, heaven forbid, to have to replace the whole force main? So the first thing that we did was we looked at what type of failure occurred with the force main. And as soon as you look at this pipe, you can see that you have an invert, but the crown and pretty much everything else of it is gone. And this is typical of hydrogen sulfide corrosion. So an eating away of the pipe from the inside, not from the outside, not a stress failure. Andy's going to talk at length about different types of failures, but this is textbook hydrogen sulfide corrosion. So hydrogen sulfide corrosion 101, I'm going to have to take you back to high school chemistry and give you a quick explanation about why this happens and why we knew for sure that this was H2S. So as sewage travels in a force main, the bugs, the bacteria, what's called the BOD, there is a demand made on the sewage to break it down. And usually it breaks down into carbon dioxide and water. And what the bugs do, the bacteria does, it uses the oxygen within the sewage to convert to carbon dioxide and water. Once that oxygen is used up, now we go from being aerobic to anaerobic, no oxygen present, and then the bacteria latch onto the hydrogen in the system because there is no oxygen left in the system. And so we end up with things like hydrogen sulfide, methane, various other byproducts, but we will focus on hydrogen sulfide. Now, hydrogen sulfide in itself isn't a problem until it comes in contact with water vapor. And then it forms sulfuric acid, which is why, as David mentioned, when you get a discharge of a force main into a manhole, that's the first place that we look for hydrogen sulfide corrosion, because in a forced system, if it has gone septic, if it has gone anaerobic, the first time the hydrogen sulfide will come in contact with water vapor is going to be at the discharge manhole. So when it goes septic within a force main, what are the conditions that make it go septic? Well, the big factor is travel time. If you've got a short force main, 300 feet or something, pumps up out the other end, and it's reaerated again as it travels through the manhole, so you don't have an issue. So it's really how long something stays within the force main, where the bugs just continue doing their work and they run out of oxygen and start using the hydrogen. So the length of the force main and the size and the pump, that calculation tells you how long it's going to take to get through the force main. And the other important factor is the concentration of the sewage. So for those of you that are treatment plant operators, you know what a BOD is, the biological demand that the sewage is making. How much oxygen do you need to break down that sewage? So obviously, if it's in the summer where you've got very low INI, say during a drought period, then the sewage is more concentrated. It will have a higher need for oxygen. But also during the summer, the temperature rises. And a really good rule of thumb is for bacterial activity is for every 10 degrees centigrade rise, that's 18 Fahrenheit, doubles the activity of the bacteria. So you get a 10 degrees, that's a doubling, you get another 10, that's a quadrupling, and so on. So it really is a big concern when you have hot, dry summers that you can get these failures. And the other issue then is elevations in the force main. If you've got a force main where the sewage remains in a flow line where there are no gas pockets at all because there's minimal change in variation, you're never going to be exposing the hydrogen sulfide, if it forms, to any water vapor until it discharges either at a manhole or at the treatment plant. So it's of a major concern is what is your flow line when the pump shut down. So now let's look at what was happening in Hanover Park. This is just one piece of the very long force main, but this is the piece that matters. Here is your discharge location, and upstream of the discharge location is one hill, and you can see when the pump shut down, this area here was above the flow line. So there was potential for gas pockets. Gas pockets could have water vapor in them, so the hydrogen sulfide could combine with the water vapor, form sulfuric acid. Then if we go 1,000+ feet upstream, so closer to the initial pump station, there's a much longer hill, and this elevation is dictated by the lower hill, so the water level is here. So this area is much longer, but it's not as far along as the last hill. So if we were going to say where it would fail first, we would say the second hill, because again, its travel time is the important thing. And this is exactly where it failed and where they repaired it. So our major concern was this hill, and we were looking originally to excavate into the pipe up and downstream, but the village were most concerned that maybe there was somewhere else that we should also be looking at because of having the whole system being vulnerable and not just these areas. And the other thing to be noted is that these pipes were supposedly coated with epoxy. When it was designed so that the areas that were considered vulnerable should be coated with an epoxy that would not be eaten away by hydrogen sulfide. So that added more to the mystery and why this is almost a forensics science study. So the pipe material was an epoxy-coated ductile iron. The specification was for a ceramic epoxy, something like a Protector 401, but there was also within the specification a bituminous epoxy, and that is important. So why did this pipe fail? Well, it could have been that the ceramic epoxy was improperly applied. Now we're going back and looking at records, almost 20 years old, and there's no longer anything available to look to. The pipes could have been switched on site because not all of the pipe was coated. So did they just put the wrong pipes in the wrong places or the right pipes in the wrong places? Or did they actually use the copper's spec, the bituminous epoxy, which is substantially cheaper than the ceramic epoxy? And we suspect that that's probably what happened. But again, there are no records at this point to say whether it was a ceramic coated epoxy or bituminous epoxy. And at this point, it doesn't matter. What the village needed to know was, did they have other vulnerable areas? So their priority was to determine this vulnerability, but to minimize inspection costs. Now, to understand inspection costs with these long force mains, this gets really expensive. But you also have to look at your replacement costs. And at the time, without understanding the system, they were looking potential costs of between 5 and 10 million, just ballpark numbers. Massive costs to replace something that hasn't been in the ground 20 years yet. So there are different technologies available to evaluate an entire main. And I say that they're a Rolls-Royce versus a Bentley because this is not like a Caddy or a Chevy. These are major expenses. So we were looking at somewhere between 200, 250,000 and getting close to $500,000 to evaluate that. But then when you look at the total replacement costs of the force main, you could understand why, given the vulnerability of this force main, they wanted to know where their weaknesses were. So the more expensive system is the electromagnetic, where you can actually look at the pipe wall thickness and it scans every 1/10 of a foot. The issue with that, or even though it tells you exactly where everything is on every single piece of pipe, is that we had to have a clean force main. And cleaning a force main is in of itself very expensive and was going to be between $70,000 and $100,000. So the other method, the acoustic detection, looks for pressure anomalies, leaks, gas pockets, but the village were aware that it would require some follow-up excavations. But ultimately, that was the system they went with. It's called Smart Ball. This is a company called Pure that they hired as a sub to do this, and they ran the Smart Ball through the system, and it identified all these things that I've listed. The main ones you want to look at, the anomalies and the gas pockets. So this is what it showed. It showed that here, which is where we had the first burst, there was a massive gas pocket. But we already suspected that, and they'd already replaced this pipe. So we know that we didn't need to go back and look at this again because we know what the recommendations are going to be for this hill. The interesting thing was the first hill were the issues where we had said that we suspected they would have issues was the area where they had issues. And so what we recommended to them after this was that they should look at the pipe at the air release valve, which is where it should be the worst because it's the highest elevation above where the water shuts down, that we should open up and look at this gas pocket here, this long one, and then we should look somewhere in the middle and somewhere down towards the end before it goes under the water. And originally we were going to do that by excavating, cutting into the pipe, but the village were obviously concerned about that because then they were putting bare pipe back in or a small repair, and they wanted to know if there was another method that they could use. And so there is a product called a BEM, a broadband electromagnetic induction inspection, which basically lays over an exposed piece of pipe. So they would have to excavate but not cut into the pipe. And then it will measure through the wall and determine the relative thickness. And from that, knowing what the starter wall is, you can get what the final thickness is. It does not require to be in direct contact with the pipe. You can still have, if you've got the poly tube around it because you're in hot soils, you can do it through that. When we exposed it, we actually removed the poly tube just because the ground and everything was so wet and tacky that really to be able to get to the pipe, it was better to expose it and put the equipment directly on top. So here are the 4 locations, the one at the vault, and then the first gas pocket, and then an anomaly that was further down, and then the second to last gas pocket. Essentially, we did this some distance of about 700 feet in total, and it looks nice and easy, but actually this is all the way through forest preserve and very high grass and trees and bushes and everything. Also right next to the major DuPage County water main was only 10 feet away, so it's not like the easiest excavations that you want to do. So we actually ended up doing 3 of the 4 locations. The fourth one, which was the air release valve, the hydrogen sulfide levels were so high that it was actually unsafe to enter the vault. And so we agreed with the village that we would not do that, even though we knew that that would actually be the worst conditions there. We exposed 5-foot sections for the other areas, about 5 to 7 feet deep. And then this data was uploaded for analysis to a company called Rock Solid, who do the BM analysis. And so we looked like heroes at the first excavation because there was a hole at the first excavation, which as soon as we had run the BM analysis, the village went and did a repair immediately. And so this is what actually the BM found at the first. We had an area besides the hole where we had only about 59% of the wall. And then the best was about 89%. The average wall loss was about 20%. So except for the hole that we had, it's an area of concern, but they haven't got to be out there repairing it tomorrow. The next area, the BM3 that we're calling it, we actually only had about 2% to 8% loss of wall. And the last area, we actually are 100% plus. So obviously walls vary in thickness. They're not all exactly the 0.4 as we expect. But this pipe, there is no loss, so this is fine. And let's go back to what the smart ball said. The smart ball said that there were gas pockets up here and all the way down to here. So we found up here we had a hole and the wall thinning. As we got down to here, we have only about 8% loss. And down here, we have almost no wall loss at all. So our recommendations will be that we replace from here through the first gas pocket and somewhere down, probably we would recommend through this gas pocket that we did not analyze till we get beyond that one, because once we start to go down this hill, the pipes are not as in bad condition. And so our recommendation is to replace between 260 and 520 feet. And that is obviously still at discussion with the village, but for sure this 170 feet, longer than they did for their repair, but to get them to the water level. And then here we would replace certainly from the valve to the force main and some distance beyond that. And as I said, probably about another 250 feet beyond that. But when we look at that in total, you're looking at replacing 520 feet out of 17,000 feet of force main. So that's only 3% of the system. So that's a significant savings over what they were originally thinking they were going to do. The valve vaults themselves are in good condition. They have been coated with an epoxy, but because they're not safe to enter, because of the high hydrogen sulfide conditions, we're recommending that they are reconstructed so they can be safe to enter. We could not enter them without removing the venting system. And once we removed the venting system, obviously it was too dangerous to enter. So we would like to reconfigure those for the village. So in conclusions, force main inspections, when we're talking about long force mains, it is a multi-step process and it can be significantly expensive. But you have to look at the cost of the evaluation versus the cost of replacement and put it in those terms. Understanding that replacement and rehabilitation of force mains can be very expensive in themselves. Because of the cost of bypass, can you imagine if you're looking at rebuilding this whole force main, how you would bypass 3.5 miles? Major, major costs. And then also constructability. We're looking, as I said before, there's also a landfill with very high elevations here that this force main goes under. There's a water area, a wetland, a river. It's really quite a nightmare thinking about having to rebuild this. And so when we look at force mains, it really is the efficient use of funds and recognizing that you have a vulnerable asset and how best you can maintain that and understand its condition. Thank you.
Great, thank you, Kathy. Our final presentation will be of the lift station and force main section will be Andy Detmer speaking about force main assessments in general.